Thank you, everyone. All right, so as Lorenzo said, my name is Antoine Cully, and I'm coming from Imperial. And as he said, I'm working on robot learning to make robots, here in my case, more versatile and more resilient. The reason why I'm trying to do this kind of research is because I deeply believe that robots have a tremendous potential for society. And literally what I want to do is to remove humans from the most dangerous tasks they have to perform. Today, we are still risking the life of thousands of people on a daily basis for tasks where we could use robots instead. So for instance, when there is a natural catastrophe, like an earthquake, we're still sending humans to try to find potential people stuck under the debris. In a mining operation, in order to collect the precious mineral to build your laptop and smartphone, we are still risking the life of thousands of people on a daily basis. Again, we can use a robot instead. We are talking a lot about spatial exploration. We want to send people on Mars or even on the moon in a few years. But the first thing we do first is to send a robot to make sure that everything is safe. And an example that I think speaks a lot is the Fukushima nuclear catastrophe that took place actually when I was doing my PhD 10 years ago. And what was interesting about this problem is that it was in Japan, and back then Japan was the house or the land of robotics. It was supposedly the most advanced country in the world in robotics. And yet, after the explosion of the nuclear reactor, the Japanese government tried to send robots, actually failed, and had to send and sacrifice retired Japanese elderly in order to intervene in the nuclear reactor and shut off the nuclear reactor. So my goal is I want to avoid this, and I want to use robots and AI in order to make the world safer. And of course, tackling problems like Fukushima, I'm not the only one on the planet thinking about this. So for instance, 10 years ago, just after the Fukushima scenario, the US government, through the DARPA agency, decided to create a competition, where they actually put on the table $1 million cash prize, brought the best mind of the planet, so people from all around the world, South Korea, China, US, Europe, Japan, and so on. And they try to compete in a parkour where robots have to do and solve tasks that resemble things that a robot will have to do during an operation like Fukushima. So driving a cart, opening a door, walking over debris, climbing stairs, drilling a hole, shutting off a valve, and so on. And as you can see, it's very, very difficult. There are always things that go wrong. Definitely the state of robotics has improved in 10 years, but actually not that much, and you will see why in a minute. But what I want to show here with this video is that even if you take the brightest mind of the planet, there are always things that you cannot anticipate. And sometimes it's some very, very silly things. It can just be that the robot ran out of battery, they lost the Wi-Fi signals, these kind of things. But while I like starting my presentation actually for the last 10 years with this video because it's lifting the mood of the room and so on, this funny video is actually hiding a bitter truth. So for instance, the robots that you see on the right-hand side here are actual robots that were sent into actual search and rescue mission in order to save people, and they all had to stop their operation after a ridiculous amount of time. Again, some of those examples are a little bit old, but the story still holds today. I love, for instance, the example on the top right here, that was a robot that was sent in La Conchita in order to explore a house after a mudslide, to see if there are some people stuck inside the house. And unfortunately, this robot had to stop its operation after only 2 minutes into the mission. And the reason is that the robot actually tried to do something extremely risky. The robot actually tried to cross the living room. And that's it. That was the end of the mission. Why? Because in the living room, there was a carpet with long hairs, and the long hairs got stuck in the track of the robot. And so the robot itself got completely stuck on the carpet. And so eventually they had to send human to save the robot that was supposed to save the human. So again, you can see there are very silly things that can happen and that can really put at risk your mission. And the goal of my research is, can we use actually AI? Can we use machine learning? Can we use robot learning in order to enable robots to go back on their feet after being damaged, after a problem? If there is a way to think outside the box and still achieve the mission, even after something goes wrong, how can we do that? So that's the kind of that's the goal of my lab in general. And just to show you that the situation has not changed a lot in the last 10 years. This was in September, just 4 months ago. And that was CoRL, so the Conference on Robot Learning. So definitely the pinnacle of what can happen and can be done in robot learning around the entire planet. And in conferences, you always have some gala and some shows, and because it was in South Korea, we had K-pop, and of course, K-pop dancing robots. And you can see that even with this kind of high-stake, high cognitive capabilities in the room, there are things that cannot be predicted. And sometimes it's quite dangerous. You can see here, it will actually smash the glass. So again, in a public event, that's not something you want to do. So my question is, how can we use learning algorithms to make robots more versatile and more resilient to be able to handle more diverse situations? So 10 years ago, I presented this paper during my PhD, which made the cover of Nature. It was actually, Lorenzo, the very first paper showcasing robot learning in the cover of Nature. Now there are many more of them. And the idea here is that this robot is a very simple robot. It's just an example robot, so 6 legs. It has 3 degrees of freedom per legs, literally just 3 motors, and a single sensor, which is this 3D camera. So it's like a Kinect back then, that gives a single information to the robot, which is basically its trajectory. And from the trajectory, we just extract the average walking speed of the robot. Okay? And this robot has a single mission, very straightforward, actually. It's to go straight forward as fast as possible. That's the only thing that this robot has to do. And right now, the robot is controlled with a periodic motion. And as you can see, the robot is intact and everything is going well. The robot works at a speed of 25 centimeters per second. But then, you probably guessed it, because I'm a mad scientist, what I did is that I removed one of the connectors at the root or the base of the leg. And because all the motors are connected in series, this means that just unconnecting one connector is basically powering off the entire leg. So the 3 motors of the leg cannot be controlled anymore. And you can see that this very tiny problem here, or situation, has a big impact on the gait of the robot. Now, instead of going forward at 25 centimeters per second, it's basically staying on spot and with a linear walking speed of 3 centimeters per second. You may think that, yeah, maybe removing a cable is something, kind of far-fetched, but it's actually a problem that happens often when you send, for instance, a robot on Mars. When I was discussing with Airbus and how they actually manage the Mars rovers that they sent with ESA, they actually are very limited in adding some straps, some covers, some plates, and so on, because all of these kind of things, to make sure things stays in place, is actually adding some weight and costing a lot of money and putting a lot of constraint on the mission. So often you just have to rely on a single connector and things can go wrong. So to go back to this Nature paper, what I proposed was the intelligent trial and error algorithm. So here you can see the robots trying a new behavior to try to find another way to solve the task of going straight forward as possible. And you can see the robot try something. Here you have the trajectory that is provided by the 3D camera. And we use this information in order to update some behavior repertoire or prior knowledge. And here what is important is everything is running in real time. Everything is running on the onboard computer of the robot. The onboard computer of the robot here from 10 years ago is probably 10 times weaker or slower than the phone that you have in your pocket. And the only thing that is happening between 2 different shots of the video is me taking the robot from the right side of the camera to the left side. And so here, in just 40 seconds of real-time adaptation, you can see that the robot found another way to walk that is not using the damaged leg, and instead is relying more on the back leg in order to push itself forward and avoid using the middle legs. And the good thing here is that if you look at the slow motion, what you can see is that it's actually a very dynamical motion. And this kind of very dynamic behavior is often hard to optimize directly, especially on a real robot, because that's something very, it's an optimization landscape that is very discontinuous, rough, and so on. So following some small parameter adjustment through gradient descent or sampling may actually be very difficult. So how did we do that? Here, there is actually no magic. The idea was that instead of starting from scratch, instead of learning directly what the robot can do from scratch after damage, we instead rely on a lot of prior knowledge that we generate in simulation from the intact robot, again in simulation. The idea, to give you an analogy, is if you have a child, for instance, and the child is playing on the playground and having fun, and if at some point they become injured, just spraining an ankle, something like this, they will not just go and say, oh, actually, I will forget everything I've learned over the last 5 years or so, and I will just relearn to walk from scratch. No. What they will do is they'll just find another way to walk, another way they already know, that will actually minimize the pain. Like, for instance, hopping on one leg minimizes my pain on the left leg, and that allowed me just to go back home. So here you can see easily that children will actually discover not just one way to walk, but actually hundreds, if it's not thousands of different ways to walk. And they will do this just because it's fun, just because it's different, not because it's necessarily useful a priori, but then they will use this prior knowledge in order to quickly adapt. So instead of learning from scratch, they will instead flip through the collection of existing walking gaits they already know to try to find the one that works well. And so this is exactly what you've seen in the previous video. Here, the robot, instead of trying to learn from scratch, new parameters and so on, the robot is actually flipping through a repertoire of existing gaits in order to find the ones that minimize pain, or say differently, that maximize the rewards of the robot. And so then, here what we tried to do was actually to change the question. Instead of asking, how can we learn something fast on a real robot? Now the question is more, how can we use our intact robot in simulation and try to discover all the different ways this robot can walk forward as fast as possible by using its leg, for instance, differently. And so for that, we had to come up with literally a new family of learning algorithm. It is called quality diversity optimization. And the reason is that in contrast with traditional optimization or learning algorithm where you try to only find a single solution that is optimal to your optimization problem or to your reward problem, here we are trying to generate a large collection in a single optimization process or in a single execution of the algorithm. We generate an entire collection. And in this collection, you will have hundreds, if not thousands, of different solutions where every solution is as much different as possible from each other solution inside the collection. And for every types of solution inside this collection, we want the best possible solution. So in the case of robots walking, we have actually a lot of different walking gaits. And the idea is that can we find a lot of different ways to use our legs, so for instance by touching the ground with different patterns, in order to discover different ways to walk. And for every types of patterns we have with contact with the ground, can we find the one that goes forward as fast as possible. And so here, what you can see on the left top corner is basically all the collections that we have generated. And the only thing you need to understand here is that it's a big matrix with more than 13,000 colored pixels. And every colored pixel corresponds to a different walking gait. And the color of the pixel corresponds to its walking speed. So the more the pixel is red, the faster goes the robot. So the first thing you can see is that out of the 13,000 walking gaits, we have actually a lot of them that are red. So this means that the algorithm found on its own a lot of ways to go forward by using the legs differently. And so here you see one example of those gaits, which is using more or less all the legs in a kind of a even fashion. But what is interesting is that you have some gaits in this large collection that are using some of the legs a bit less. So for instance, the legs that are circled in red like this are in contact with the ground less than 10% of the time over the entire episodes of evaluation. So that's cool. We have some gaits that are actually more looking like a quadruped gait rather than an hexapod one. But what's interesting is that when you look at those 13,000 different solutions, some of those solutions start to be quite creative. So for instance here, my simulator told me back then that this walking gait had actually a good performance, a good walking speed, but was in contact with the ground with none of the leg more than 10% of the time. Back then, I was literally a PhD student, so my first reflex, probably like you, is that there is a bug in my code, right? I need to go back to my code and fix it. But before doing this, I decided to just render the video to see the result, and this is the result. The robot just discovers that a nice way to solve the task is to flip on his back, walk on his knees, and that's yet another way to solve the task. The thing is that I was just detecting contact with the tip of the leg and the ground, not checking with the elbow, but that's yet another solution. So here you see that just by trying to search for a lot of different solutions, not necessarily only things that are highly performant, but also the notion of diversity, we can find some very creative solution. All right, so this is for the high-level objective and what we did in this Nature paper, but now I will give you a very brief tutorial to show you how we can generate this kind of large collection of solutions. And what is interesting is that I will cover and I will present an algorithm that is called MapEdit. It's a 5-line algorithm, and it's a very, very, very effective algorithm. I will come back to this a little bit more in 5 minutes. Just one thing, if you have any question, feel free to interrupt me, raise your hand and so on. There are not that many people in the room, so we can have a very interactive session if you have anything. So, as I said, let's go into this quality diversity example. We have this biped robot. If you played with OpenAI Gym, you probably have seen this guy a million times. And so you know a very traditional reward function or fitness function, which is the forward speed minus the energy consumption. Just maybe words of definition here. What I call fitness is basically the total, or it's equivalent to the reward, but it's computed over the entire episode. So it's basically a reward score, but that captures everything that happened from the beginning of the episode to the end. You probably heard or used reinforcement learning definition of reward, where you have a reward value at every time step. And so the link between the fitness value and the reward is usually just the sum of the reward over the entire episode. Or if you do some statistics, you can also compute just this as the expected sum of reward, which is also known as the expected return. So you can see in your mind that the fitness is just another term for expected return. Okay? So far, so good? So here we are very, very similar to deep reinforcement learning scenarios that you have seen probably many times already. But the big difference when we start to step into quality diversity is the second line. We want to generate a collection of different solutions. So we need to define some things that will tell us what are the different types of solutions. And for that, we use something that we call a descriptor or a fictive vector or behavioral descriptor or behavior features. It's just something that characterizes what happened during the episode. Here, our goal is to take this legged robot and to teach it how to walk forward as fast as possible while touching the ground differently. So a very traditional way of doing it that I introduced in my Nature paper, it just considers the proportion of times that each leg is in contact with the ground. We have a biped robot, so 2 legs, and so that means that the descriptor vector will be a 2-dimensional vector, where the first number corresponds to the number of time steps over the entire episode that are in contact with the ground with 1 leg, and the second dimension, the same thing for the other leg. So far, so good? So in quality diversity, what we want to do is to fill a sort of collection like this. So here, my descriptor space, because it's a proportion, it can go only between 0 and 1. Okay? And so here you see the space between 0 and 1 on the 2 dimensions. And then map it, or in general in quality diversity, what we do is that we discretize this space into cells using a grid. You can use a Cartesian grid, with very orthogonal cells. Here we use central Voronoi tessellation in order to create the cells. It looks fancy. It has some very good properties in high-dimensional cases. But if you don't understand why that's the case, just imagine that they are very nice squared cells instead. Okay? And so our goal in quality diversity is to fill every single one of those cells, or as many cells as we can, with the best solution we can generate. So typically, we would like to have a solution like this one, that are using more or less the legs equally, and that are working quite fast. We may want to generate also the opposite solution, that is actually dragging one of the leg and using the other leg to try to propel itself forward. Here we have the opposite, so it's basically just hopping on one leg and definitely not using the other leg. And then you have the robot from Monday mornings that is dragging its feet to go to work. All right? So the goal is really to try to cover all the different trade-offs and all the different ranges of solutions that we have here. And so in order to fill this archive, I will introduce you to the map-it algorithm. It's a 5 lines or 5 steps algorithm, and it's very, very powerful in a sense that right now, you can just let it run longer, and it will eventually catch up with all the state-of-the-art that we have in quality diversity. But I will come back to some of those a little bit later. So first, how do we initialize this algorithm? You create a grid like this, so just an empty big table, in your software, in your program, and then you will just initialize the state of this grid just by randomly generating, 100 solutions. You will evaluate those 100 solutions. You will record for each solution the fitness and the descriptor, and you will just add the solution and the fitness to the corresponding cells according to the descriptor. So for instance, if you have a descriptor that says the legs are used 0.6, 0.4, you will place it somewhere here, and you will just have the values that corresponds, the value of the pixel corresponding to the fitness. And that's it. So that's the initialization. And then the main loop of the algorithm that you will repeat thousands of times just involve randomly selecting some solutions that are already in the grid, applying some mutation. It can be just Gaussian noise on the parameters of your solution, on the weight of your neural network, or whatever you're trying to optimize. Then you evaluate the solution. So here again, you record two things, the fitness and the descriptor, exactly like you did during the initialization. And then you add the solution back into the grid, the new solution back into the grid. So here you have two possibilities. Either the cell corresponding to the Beer descriptor of a solution is empty, like this one. And so here in this case, the situation is very simple. You just add the new solution into the grid. So that's a great news. You just expanded the coverage, expanded the diversity of solutions that you have in your collection. That's great. The second situation is if it's landed into a cell that is already occupied by something. So here again, very simple solution. You just keep the best out of the two solutions. And so if the new solution is actually better, you take the old one, you throw it away, you replace it with the new one. That's again a very good news because this means that you improve the performance of the solution contained in the grid. And you repeat this selection, mutation, evaluation, addition step, as many times as you want until it converges, and you will generate some of the solution. That's literally the algorithm that I use in the Nature paper. And so that works well. But of course, here, and back then, 10 years ago, that was the case, we have a challenge linked with the curse of dimensionality. If you have a parameter set for your solution, like if you do, for instance, some sine wave control, so your motors are all controlled with sine wave, and each sine wave is configured by a few parameters like the amplitude, the phase, things like this. You may have like 20 parameters to evolve, and adding some Gaussian noise may be sufficient. But today, with modern reinforcement learning and even more now with LLMs and diffusion policies, we have policies that are more in the order of tens of thousands of parameters. And of course, adding some Gaussian noise is not the best solution to handle this. So over the last 5 years, actually, my team tried to take all the concepts that we have developed around quality diversity and to try to scale them up to a large policy. And the way we did it was to actually combine the map-it algorithms that I mentioned with modern policy search or deep reinforcement learning, literally TD3, PPO, and SAC. So here, my goal initially when I started this project, or this line of research, was to try to think that the evolution, so just adding Gaussian noise and searching for diversity, will promote the creativity of the results, while following gradient and using deep reinforcement learning, we'll try to instead optimize the solution and do some fine-tuning of the solutions that we generated. The idea really was to try to bring the best of both worlds. And so the first attempt of doing this was already 5 years ago, and we won the Best Paper Award, where here you can find the same map-it loop, the same foundation. So you randomly select some solution, you randomly select them, you apply some mutation, you evaluate them, and based on the evaluation, you add them back to the grid. But here what we added is this additional line where we said instead of mutating with just some random Gaussian noise, what we can do is to apply some gradient, some policy gradient steps in order to improve the policies following the gradient that is provided by a critic. So here it's a critic from a TD3, so we have a replay buffer and we have an actor and a critic, and we use a critic in order to infer the gradient that we want to apply to all the solutions that we mutate. Here the good thing is that we use an off-policy approach, so we can apply the critic and deploy it on any types of policy, even if it's not the policy of the actor. And so here what you can see is that now we can actually solve this problem of generating large collection of solutions for very complex robots using, so I think here in those videos we have 20,000 parameters that we optimize. And actually from this point onwards, the dimensions of the policy was not a problem anymore. So we have done on 10,000, 20,000, 70,000, and beyond that is actually pointless. So now we can just scale to any dimensionalities that we want. And if you look at some results of performance we can get between this one, so on this task, like in the tutorial, this is what map-it gives you. So it gives you a very large coverage. It finds all the different types of behavior, but the performance overall is very bad. We don't really have a solution that is working efficiently on straightforward. Well, if we use PGA, which means policy gradient assisted map edit, we can see that we have the same coverage but way better performance. So that's quite exciting. But there are some limitations with this approach. And the main limitation is that if we consider, for instance, this robot here, the quadruped robot, but this time, instead of trying to go forward as fast as possible, we change the task definition. What we want to do now, the fitness or the reward is strictly to just minimize the energy of the robot. And the descriptor is the final location of the robot at the end of the episode. So what this means is that we want to find a large collection of different policies. Each policy is being specialized in going in a different direction. So it's basically allowing the robot to go in different direction in an omnidirectional way. But we want, for each specialized policy, we want the most energy efficient one. Okay? And for instance, if you take a solution like this one, working quite well in one direction, we can assume that it is quite efficient in terms of energy. And you apply the policy gradient mutation or variation operator. So you take the critic that you have trained through your actor critic methods, and you just change your genotype or change the weight of your parameters in order to get a new solution, but by following this gradient. This is what you obtain. Do you know why? It's because the best way to be energy efficient for a robot is to not move. So here, actually it's not even a joke, this is a video. The optimal solution if you follow the gradient of optimizing the energy efficiency is to not move. That goes completely against our objective, which is to go as far as possible in different directions, to try to discover more solutions. So this means if I take a solution like this, and I follow the gradient, I will actually be forced to go back to the initial point, and so basically limiting all the learnings that I can get. So if I return to the same slide as before, you can see still a very good improvement between MapEdit when we want to go forward as fast as possible. But as soon as we change the task definition here, in this case, following the gradient goes against the diversity we are looking for. And so here you can see almost no difference because in practice, following the gradient here almost doesn't help. So in order to fix this, we published a couple of other papers, including this DCG MapEdit paper 2 years later, which got again another Best Paper award. And here you retrieve the MapEdit foundation. But here's the key idea that after every evaluation, we store all the transition we observe in a replay buffer. But this time, for the actor critic algorithms that we train, still TD3 if you want to know the details. The key difference, so here you have the critic, here you have the actor, but the key difference is that now you have this small d. So this means that here, the actor critic that we train is actually conditioned on the descriptors that we would like to have. So this means that now if I have a solution that goes very far in this direction, I will ask the critic, can you give me a gradient direction to follow that will improve the performance, but that will continue to lead me toward this direction? That will maintain basically the skill or the type of behavior that I had so far. And if I'm, for instance, here, if I have a BD or descriptor that is 0, 0, it will say, oh, can you just give me the best way to improve my energy efficiency while staying at 0, 0, things like this. And we have this for both the actor and the critic, because you need to, the actor needs to know what is the task that the critic wants to improve when you train it.
Sorry, can
Sure.
you remind me again what is the descriptor?
The descriptor is just the skill descriptor. So it depends on the task. It can be the proportion of contact with the ground, or it can be the final location, depending on the example. So it's basically what kind of skills do you want to exhibit.
So it's a label for what kind of skills?
Exactly.
Okay.
Yeah.
But then you keep all of the descriptors so the model then will have the descriptor as the input when you generate the policy, or is different models? So
the descriptor, generally speaking, is something that you observe at the end of the episode. So you roll out a solution and you observe it literally like you observe a reward or a fitness. You just observe some other trajectory, and from the trajectory you infer some, or you define some descriptor. But here in this case, your comment is important, because when we want to know the descriptors that we want to feed to the critic to know the policy gradient or the gradient we want to follow, we need to know this D in advance, right? And here's the idea that we just take the descriptor of the parent. So the idea is I have a solution that have been generated in the past. I don't know, it's already in the archive, but I just take it and I want to mutate it, or I want to apply some variation so that then it's getting better, just following the gradient. And for that, I just take the descriptor of its parent, so to tell the policy to continue to execute the same types of behavior, but improving the fitness. So it's basically trying to find the orthogonal projection between the two. Does that make sense? Good for everybody? And just have one last slide here, which is now that we have this critic that is conditioned on the descriptor, we can apply a policy gradient variation that is now informed with the skills that the initial policy was executing. And the good thing is that now we can actually tackle a lot of different complex problems. So here, if you remember the case of this quadruped robot, that was the normal map edit, that is PGA map edit, and this is DCG map edit. So basically now exploring the space is not a problem anymore. We can actually reconcile the policy gradient and the exploration and the diversity. And we are very happy with this kind of result. And the results are just out of the roof when compared to the other methods. One thing that is interesting just before I close this chapter is that, as I said, we need to have like the critic that is descriptor condition in order to know how to apply the policy gradient variation here. But we also have the actor that is descriptor condition. And the actor and the critic are trained together just from the data that is generated during all the evaluation. What is interesting is that actually this actor, which is here just to guide the critic training to tell, okay, this is the best action that we need to follow if we want to continue in the episode. Here, in a sense, we have to train this actor that is descriptor condition. And that is very interesting because this just means that we have an actor, so a single policy that takes as input a desired skill that can actually execute any of the skills that have been seen before. So in a sense, that naturally distills all the different policies that have been explored, like the thousands of different discrete policies that we generated, into a single policy that can be used to execute an arbitrary things. And the good thing is that it comes at no additional cost because we needed to train this in order to train the critics that was needed to generate the whole collection. So in a sense, it's a very symbiotic relationship where in order to generate this collection, we need this, and in order to do this, we actually need to discover all this collection. So yeah, so that's a good approach to distill the entire collection into a single policy. And as I said, at no additional cost. So now, just to return a little bit on my initial intuition or motivation of doing this in order to bring the best of both worlds. Here, so to just remind you, I was hoping that the evolution will drive the exploration, and the policy gradient or the policy gradient variation will try to optimize the solution. So is it really what is happening here? Well, actually, no. And I was very surprised when I started to look into this kind of result. Just to give you a sense quickly, so here we have two different ways solution can be mutated or can be varied. One is just adding some Gaussian noise. One is just adding some or following the gradient, right? So this means that during the full process, we still have the two operators, the two variation methods that coexist and just apply different solutions. So a question that we ask ourselves is, in order to fill this archive, how many of those solutions actually come from this genetic variation algorithm or variation operator? And how many of those come actually from the policy gradient? The idea is that if it is if the policy gradient is actually improving the solution, we will see a slow improve, iterative improve over the entire duration of the training. And conversely, the genetic variation will find some solution at the very beginning and then will die out because we cover the full space, and we observe this quite a lot. It's often the way quality diversity algorithm works. They cover the space very quickly and then they improve the performance across the board. But the intuition was this initial cover-up would be due to the variation operator, and then the refinement over time will be done by the policy gradient. And so when we actually try to plot these experimental results, we can see that it's literally the opposite. So here you have 4 different tasks, and you can see at every time, this is the entire execution of the algorithm. So we have millions of time steps overall. millions of evaluations. So here you can see, according to the number of evaluations we have done for the full learning, you can see the contribution in blue of the genetic variation operator, and in orange of the policy gradient variation operator. And you can see that actually the just naive Gaussian noise is providing way more solution to the archive than the policy gradient. Policy gradient is helping a little bit at the beginning, even nowhere near the genetic algorithm variation, but is dying out very quickly. And so I found this result very, very interesting because this really means that my initial intuition was wrong. And instead, if you want to learn more about this, my intuition or my hypothesis about this observation is that this is more linked to the lottery ticket hypothesis. I don't know if you are familiar with the lottery ticket hypothesis. Do you know it? So the lottery ticket hypothesis is a very interesting observation that says when you train large neural network, there is this notion that the curse of dimensionality will make your training more complex as the number of parameters grows. Okay? But in practice, we have observed that it's not always the case. And sometimes just training larger, significantly larger network, like 10 times larger, will actually make the training task easier. And the reason is because inside a huge network, you have a lot of tiny networks. You can just say, imagine if you have like a neural network with 1 million parameters, and you set half of them to 0. It's equivalent to having a smaller network, right? You can also imagine that you have all the left-hand sides that are non-zero. You have the middle of your neural network that is 0, and the right-hand side that is non-zero. It's literally like having 2 independent neural networks. So in a sense, inside a big, big, big neural network, you have actually many neural networks that can coexist. And so here, the idea of the lottery ticket hypothesis is that maybe when you train a very large neural network, you have actually a lot of small neural networks that all are like a lottery ticket. And maybe one of them is actually closer to your local optimum that you're looking for. That it becomes very easy to train because you don't have to deal with exploration and so on. You just pure small exploitation and you get it. And so here I think it's probably something like this. What happens is you have a large neural network space, it's very complex to explore, and in this very large subspace, there may be a subspace that is actually promising, actually containing meaningful and viable solution. And here, the gradient is actually pushing the entire search toward this subspace, making the rest of the optimization way easier, making actually some just random Gaussian noise effective in this small space. And if you are in the right location of your search space, actually, it can be quite effective. And conversely, I think near the end, what you observe is that following the policy gradient is actually not that effective. And the reason is that you should not forget that policy gradients, when you do TD3 and so on, the gradient that you get is actually a gradient from an approximation of an approximation of an approximation. Because the critic is just here to approximate the objective function. The actor is here to approximate the best action to do in this hypothesis or abstracted and approximated representation and so on. And so trying to follow a gradient of an approximation of an approximation of an approximation is probably a little bit noisy and not very reliable when you are dealing with fine details. And in this kind of case, maybe just randomly exploring with a little bit of Gaussian noise may be less biased and may allow you to find some good solutions too. So that was a very interesting insight that I found and I wanted to share with all of you. Good. All right, so that was a lot of toy problems. So now we can show you a little bit what we do. So that's a demo that we have in the lab where we deploy this kind of concept on a single policy that is capable of doing a lot of different tasks. So for example, that's a single policy where you can control the robot to move in every direction at different speed. We can also control the elevation of the torso, the aidings of the torso. We can change the spacing between the legs. We can change the frequency of the movement. We can see the amplitude of the movement. We are robust to a variety of perturbation, like you can walk on grass, can be pushed, and so on. So this is inspired from a work that is called Walk These Ways, that is very famous. But the key things that we added to this work is, again, what happens if the robot becomes damaged. And so we try to teach this robot how to walk with only 3 legs instead of 4. So here, again, with a single policy, you just use a joystick or the controller. And after a press of a button, you can switch to a different types of, or one of the 3 legs being damaged, and the robot will continue, still remaining robust to pushes, to some obstacles, and so on. Here, if you want to know, the robot is blind as well, so it's just reacting to this kind of perturbation like the mattress just by using proprioception. So it just uses the IMU in the body of the robot in order to overcome this kind of situation. Okay? Good. A quick chapter also on quality diversity and hardware acceleration. I think it's quite exciting today because there are more and more people, using GPU in order to accelerate robot learning. Especially over the last 3 years, there have been like more and more physical simulator running directly on GPU instead of CPU. Typically, if you have heard about Isaac Labs or Isaac Sim or Mojuko XLA, not Mojuko, the normal Mojuko is on CPU, but Mojuko XLA runs on GPU. And the key thing that this kind of simulator offer is that instead of simulating one robot or dozens of robots, if you have a good CPU with 10 cores, you can actually simulate hundreds, if it's not thousands, if it's not dozens of thousands of robots in parallel. And the key question, so here, on CPU, very tiny number of robots. On GPU, you can augment this by 1 or 2 order of magnitude. And so if you can batch more evaluation in a single batch, that's great. That means you can generate more data. But there is a key question in the case of quality diversity, and actually that's the same question with deep reinforcement learning, which is those algorithms are very iterative algorithms. So you try something, you roll it out, you get the new results. From those results, you find a new mutation or a new gradient step, and you iterate like this. So if I tell you, oh yeah, we have a budget of 100 or let's say 1,000 evaluation, right? What do you think would be more effective? Shall we try to create 100 batches of 100 iteration with batches of 10 solution, so to have a total of 1,000? Or shall we do the opposite? Have just 10 iteration, but with a batch of 100? The good thing is that if evaluating 100 robots in parallel takes the same amount of time as evaluating 10 robots in parallel, this means that I don't need to do 100 iteration, I can just do 10. But of course, if it's an iterative process, if it's a gradient descent algorithm, if you follow a gradient descent algorithm for 10 steps, and if you follow a gradient descent algorithm for 100 steps, do you think you will get the same result? No, right? You will not. Because indeed, that's an iterative process. The same thing with natural evolution. If I say, oh yeah, we have, this species evolved for hundreds of thousands of generations, and if I then say, but this one just for 100 generations, you will think that this one is less evolved, right? So just having GPUs, just cramming more bigger batches of robots can allow us to generate more data faster, but it may actually hinder the learning algorithm because we are kind of diminishing this iterative aspect. So here, just to show you some framework to do robot learning or robot evolution using CPUs. This one is CPUs, this one is C++ with CPUs, and the one using GPUs, you can see that you can scale way faster, so creating way more generation, way more evaluation per second, like almost a factor of 2, so 100 times faster. But the question was, okay, and with quality diversity, what is the loss that we get if we have larger batches for fewer generation? So we tried this. We have the same experiment that you have seen before. We have this kind of very standard graph that we commonly use in quality diversity papers. So that's the number of evaluation that we do, so number of evaluation. And here we have the QD score. The QD score is just the sum of all the fitnesses of all the solutions in the grid. So the more solution you have in the grid, the larger is your QD score. And the higher or the more performant the solution are in your cell, the larger is the QD score. It just assumes that the fitness is strictly positive, which is often the case. And so the larger, the better. And so here we ran the same experiment, okay, with the same budget, so they all have 1 million evaluation, okay? But the key difference is that we changed the way we batch those evaluation. Either we did a large number of generation, but with batches of 4,000 evaluation of 4,000 robots in parallel, and we then double this number up to 131,000 robots in parallel. And then we compare the same, so we compare the QD score of those 5 different variants, but we plotted the same results, but according to different x-axis. So this one is according to the number of evaluation. This one is according to the number of generation. And this one, and of course the number of generation times the batch size is equal to the number of evaluation, if you follow. And here is according to the time, to the wall clock time. So how long it took us actually to run this on, I think it was A100 on Google Cloud. And so what you can see is that if you just look at the pure number of evaluation, you can see that actually the results are almost equal. There is a little bit of loss, but it's nothing, right? So this means that here we just show that quality diversity can parallelize almost naturally with no loss, no diminishing return. It just means that if you can fit more robots in your batches, you will actually get the same results for a lower amount of time. Here you can see, naturally, as we increase the size of the batch size, given that we have a number of evaluation constant, this reduces the number of generation. So at the end here, if we go for 131,000 robots in parallel, we have, I think, something like 10 generation. So in only 10 generation, we were able to go as much as what a robot with more than 1,000 generation was able to achieve. And of course, because we can parallelize those evaluation on the GPU, the runtime is also significantly shorter. This means that if tomorrow NVIDIA releases a bigger GPU, and they did a lot since this paper, our algorithm can go faster and faster, almost with no diminishing return, or at least not in the range that is currently feasible with our hardware. To give you a little bit of perspective, the Nature papers that I showed 20 minutes ago, it needed 2 weeks of compute on a quite beefy workstation. Now we can get the same results on a Google Colab notebook in 4 minutes. So that's the kind of scale that this kind of parallelization enabled. And if you want to learn more or to play a little bit more with this kind of tools, we have an open source library that implements all the state-of-the-art of quality diversity directly in JAX, so directly deployable on GPU using the Bragg simulator that is now called Mojuko XLA. We also try to compare this kind of hardware-accelerated implementation of quality diversity with hardware-accelerated implementation of unsupervised skill discovery papers from the literature. But this time, we said, instead of comparing the total number of evaluation or time steps spent in the environment, we can compare the wall clock time. Because one issue we have with different reinforcement learning algorithms, that if suddenly tomorrow you have 1,000 environments that run on your GPU, this means that now, instead of one environment, this means that now you have 1,000 more transition that is coming in your replay buffer for the same amount of time. So this means that you have 1,000 more transition to process through in order to train your actor and your critic. This means that suddenly your training phase becomes 1,000 times slower than it used to be. And the question is compared to quality diversity, where in some algorithms like MapElite, there are actually no loss because you don't need to do any training. You just evaluate, add some Gaussian noise, evaluate, add some Gaussian noise, and so on. And here we just compare by saying, okay, what if we just put a time budget of 2 hours and we see which algorithm performs the best. And we have run a big benchmark, and as you can see, all the methods that are on this side of the board are way more populated than the others. And it happens that it's all the quality diversity methods because it requires way less compute for training the policy, and it's way more leveraging the scalability of the environment instead. All right, I have still a lot of things to show you, but I will go a little bit more high level this time, but feel free to ask me if you have any technical question. Happy to dive into this. So some of the real world applications that I did recently is I worked a lot with DARPA, so from the US government, on the LINK project that means learning introspective control. And the idea was to try to tackle the situation a little bit like what happened in the Suez Canal a couple of years ago. I don't know if you remember, but we have these container ships that got stuck in the Suez Canal, blocking most of the logistics of the entire planet for weeks, if it's not months. What you probably don't know is that this was actually a control theory issue. What happened is that, so this is a quite narrow canal, and on that day, there was a very significant wind coming from the side of the boat. So if you are a captain driving a boat, and you have a very strong wind coming on your side, what you have to do in order to maintain controllability is to accelerate, because you need your boat to go faster than with the wind going on the side. So that's what the captain did, and he was right to do so. But the issue is that this canal is actually quite narrow, and this is probably the biggest boat that you can have on this canal. And if you have, so basically a boat going fast in this narrow canal creates actually a very high-speed stream of water going in between the boat and the edge of the canal. And high stream of water creates what we call the Bernoulli effect that basically sucks the robot toward the troll. And so by doing this, it was actually pulling the boat towards one of the edge of the canal. And of course, you probably know this, from your automation courses, that if you start to deviate, what do you do as a controller, as a PID controller? You overcompensate in the other direction. But by doing this, you get closer to the other edge, which causes another Bernoulli effect on the other edge, and basically pulls the boat and so on. So that's why eventually it went into oscillation and crashed on the edges. So the idea of this project is, if we can provide some information to the pilots, so if we can detect what is happening, provide some information, and even reject this perturbation automatically for the pilot that may have avoided this situation. So this is what we try to do. So here we have an old army robot, that's literally a mind-diffusing robot that we have in the lab. And we developed a method that is called FLARE. Just got accepted actually last week in Nature Communication, where we allow the robot to try to understand what are the consequences of its action, detect any discrepancy between what the user wants to do and what the robot is actually doing it, and then automatically learn a model of the discrepancy that makes sense, a sort of automated diagnostic, and update the control rules of the robot in order to reject automatically the impairment. So here, for instance, what you don't see is that actually one of the track of the robot is impaired. So instead of going at the desired speed, it's going half of the desired speed. So meaning that the robot turns a little bit less effectively. When you want to go forward, it's actually drift on one edge, on one side, and things like this. There are also some nasty things. Actually, hard plastic on wood kind of slip quite a lot. So that's why just effecting or executing the exact turns that you want to do is actually very difficult. And with our system, we can do it way faster than human pilot without our system. But what is interesting in our work is that we did everything with onboard compute, and we tried to do this kind of online learning with almost no prior of what is happening, so we don't know what kind of damage. But we do this in a very, very short amount of time. So here, in only 2 seconds, between the time the robot experienced the impairment for the first time and the time the impairment has been effectively corrected, it took only 2 seconds to reject this fully. Only using onboard sensors, so we have just onboard compute, we don't rely on motion capture data, except to collect ground truth for the sake of the paper. And the good thing is that when the robot returns, it's actually remember what happened and automatically recover. Another example here is that we have a wind, like a virtual wind coming in a fixed direction, and we have this virtual sail, and basically depending on the orientation between this wind direction and the orientation of the sail, we have the steering of the robot that goes a little bit in the opposite direction. So if you want to go forward here, because you have the wind, you actually go towards the edge. And so for a human, it's actually very, very difficult to drive because you want to go somewhere and you have to stop. And every time you move a little bit, that changes your state. So it changes the orientation between the wind and the sail, so changing the effect of the impairment. It's that very, very, very mental load consuming in order to drive this. With our system, this is learned automatically by the model internally and being completely rejected. So this is a quick video. So that's an experiment we did in New Mexico in the US, where we had like a massive treadmill that is actually, it was used to train big humanoid robots 10 years ago. And here the idea is to simulate the the Suez Canal. So the treadmill is a canal, the edges of the treadmill are the edges of the canal, and what you don't see is that we have motion capture sensors that, depending on the position of the robot on the treadmill, will actually induce some drift movement that simulates the Bernoulli effect. And so here we had our system that was allowing a human driver to operate and do this kind of slalom between the fake yellow obstacles that we were meant to avoid. The way it works is that we have the real robot collecting data sets and curating the data set, cleaning the data set, aligning the time series between the different data sets. Then we were learning, so we were checking that we are staying in the same condition. So if we suddenly realize that something has changed, we reset the full mechanism. Otherwise, we continue, because if you can have an impairment and then suddenly a second one, and the data you collected 5 seconds ago may not be accurate or relevant anymore. And then we had a key idea of doing some global optimization to have some knowledge that span across the entire system, and then some local adaptation where you may have like just a small edge cases that you needed to tackle. And then we were deploying the robots. And the key idea here is that we are not changing the low-level controller of the robot. We are just doing a mapping between what the user sent to the robot and what the user should have sent in order to reject the impairment. So this means that we are basically sitting at a higher level of the hierarchy and still relying on all the low-level rejection capabilities of the low-level parameters. And in general, that works quite well. So we have compared to different approaches. We have the driver and our driver, and we have without the perturbation, and here you can see that we managed to reduce the impairments quite significantly in all the cases we have explored. Another line of work, still part of this Link project, is another project that we call TrustLine, where the idea is to use world model and real-time condition in order to be able to detect if anything wrong happens to a robot. So you operate a robot, here we use a robotic crane, and if something wrong happens, we want just to be able to flag this to a red light. So here, for instance, if the movement of the payload starts to be too dynamical that we cannot predict, or that start to be a little bit dangerous, we can flag it. If someone interferes with a payload, we can also detect it and flag it. If we have, so the video continue for a few seconds. We also have, if someone drags a payload, we can also detect it. And the way this approach works is by learning a world model of the system and trying to understand if the world model configuration has changed or if the state that we predict differs a lot from the predicted state, from the observed state. What is interesting as well is that if there is some impairments or some motors, some sensors not behaving properly, we can also detect it. All right, so that's kind of standard anomaly detection. But what is interesting is that here, the key idea is that we do it in a completely passive manner. We actually don't have access to the system we monitor. Instead, we use a sort of CCTV camera to look at the system and try to infer the state of the system and use this in order to undo impairments. So here's the way it works. We have some anomaly recognition, and this is done by two things. We try to automatically parameterize our world model, and we try to predict what will happen in the next 2 seconds, and we can compare our prediction with the real world, and we can detect this. And we can flag this if there is any discrepancy. So here is, for instance, the kind of state information that we obtain. So we have the full information about the crane from those markers, but we also have, I think it's a YOLO-based method where we track the position in 3D, actually in 6D, of the payload, and we also track the position of the end in order to know what the user is doing. And the good thing is that in all the tests that we did, we tested more than 240 different scenarios. We have very good accuracy, either just on payload collision and or payload impairment or manipulation, and on motor degradation. And when we consider both of those cases, we have 93% accuracy when we use motion capture data, but when we use CCTV-like data, we still have a very good performance. And I think that those are not the latest results. I think we have slightly better now that we submitted the paper to ICML. As I said, it's a world model, so it's literally creating digital twins. So this is a digital twin that we created. You can see the solid robot is the ground truth data, and the shadow robot is the prediction. And here it's very small, and we have, after 2 seconds, only 3 degrees of inaccuracies. And the last thing we do, in addition to just flagging that there is an issue, we also provide a diagnosis of what is happening. And so here we are correct in identifying what is going on with an accuracy of more than 96%. All right, I have still a few slides. So we talked a lot about quality diversity. You probably have noticed that one key difference between quality diversity and normal reinforcement learning is that we need this descriptor that we mentioned, right? We need to define it manually. But what if, instead of doing this, we let machine learning design or define the descriptor for us? What if we use unsupervised machine learning in order to see if we can actually discover all the capability of our robots in an unsupervised manner? So this is what we did a couple of years ago with an algorithm called Aurora, and we just used an autoencoder to try to take all the skills, all the behaviors that we observed, project this into a latent space, and use the position in the latent space as our descriptor. And the idea is that we do some map-edit loops that will fill the collection. Then from this collection, we project everything into a latent space using an autoencoder that redefines our descriptor space, and we loop like this to have like a good synergies. And the good thing here is that we are not making any assumption of what kind of behaviors a robot can discover. So in this work, we just fed the entire 6D trajectory of the robot throughout the entire episode. So potentially discovering any types of trajectories that the robot can execute. And the first result that we found is that the robot can walk on a flat ground in almost all the directions. It's not very impressive, but we are quite happy because it's actually what human engineers usually handcraft. So this just means that this kind of unsupervised approach just rediscovered what an engineer will do. But then we continue to dig into the collection of solutions we discovered. And what we observed is that the robot also learned how to stand up. I did not know that was possible. I'm the one who created actually this simulation, and I was never expecting this will be possible. But what was even more surprising is this next behavior. So just in case you are tired, that we've been talking with about legged robot for more than an hour now, you know that actually robot can also learn how to roll. This was completely unexpected. Again, no prior knowledge about what can happen, and it's just another thing that the robot discovered on its own, just by leveraging the creativity of quality diversity and the unsupervised capabilities of autoencoders. I haven't talked about this work called QDAC today, but it's basically the same idea of quality diversity, but done only in pure deep reinforcement learning, kind of sophisticated constraint-based deep reinforcement learning. But here we try to do the same thing with papers that we got published at QRL last September. And the idea was to use the Aurora algorithm that I just showed you with this QDAC approach that allows to do quality diversity in a single large policy, and also using world model in order to do some data efficient training. Here, what is very important is that compared to all the work that I've shown you before, even probably compared to most of the work you have seen before in deep reinforcement learning, this work doesn't rely on any physical simulator. Instead, we will actually deploy the algorithm directly on the real robot, and we will see if the robot can discover all its capabilities, all the kind of behavior it can execute, without any prior knowledge of what kind of behavior, without any prior knowledge of the simulator, without any prior knowledge of the type of robot it is. So we just provide the information that basically the API awaits for 12 actions commands, and the state estimation is a vector of, I don't remember, 30 dimensions, something like this. And so it's literally treating the robot like a black box, and we want to try to discover if the robot can learn how to walk, how to execute different behavior, a little bit like a child discovering how to walk in the world. So first of all, we can try to make the task a little bit easier just by saying, okay, we know a little bit what we want, and we want to see if the robot can walk at different speed and different angular rotational speed, angular velocities. And so here you can see that after 5 hours of training exclusively on the real robot with no access to a simulator, the robot learned how to stand up and walk and turn in different directions. You can change the skill, request to go in a different direction, and it just goes, and so on. And so here we use some prior but what we want to see. So forward velocity and angular velocities, like this. But we can also, as I said, remove this prior and just say, discover whatever you want. And here, the interesting aspect is that there is literally no incentive for the robot to stand up but it's completely open to discover anything. The only thing we as a robot is to stay up, so on its belly as much as possible, just for saving the robot's integrity, because at some point it's become quite dangerous for the robot. So here, after 1 hour, the robot learned how to crawl a little bit. The only thing we do here, it's a pure real-time training. We take the robots from the edge of the arena back to the center, again, to just make sure that the robots remain safe. And after 5 hours, the robot learned some form of locomotion. Again, so here you can see a couple of examples. So again, we create this kind of archive of different types of locomotion. They are not very impressive, right? They are not really standing up and walking in an effective way. But just remember that this robot has no prior knowledge of his own body. It's literally like a human baby after 5 hours. They are definitely barely able to even just move their neck. So here we can frame this kind of interesting result as superhuman performance, even if it's not what we would expect. But what is interesting is that this robot just discovered a lot of different ways to walk, and we can still use the same principle to see if the robot can overcome mechanical failures. So if we break a leg, so here again we would just damage the rear leg, and we can use the same algorithm that I introduced you an hour ago just to try different behavior from this collection, to try to see if there is one behavior that goes forward as fast as possible. And here you will see after 2 iterations, still drifting to the sides, not great. After 3 iterations, still drifting a little bit. After 4, it's getting slightly better, but still not there yet. If I remember correctly, it's actually looking quite good. So maybe it stopped at 4, not at 5. Yeah, so okay, it stopped at 4. So at 4 it was not too bad, and it was able to recover from, again, a mechanical failure. All right. And the last few things I want to show you is something different. So we have talked a lot about creative diversity to try to train policies and train our robots to execute different tasks and so on. But we can use the concept of creative diversity to flip the problem around. What if we have a fixed training algorithm like your PPO or T3, your favorite different reinforcement learning algorithm? And what if we use the creativity of creative diversity in order to generate a large collection of different and challenging training environments or different reinforcement learning tasks? And so last year we introduced, it's actually got published now, we introduced the OmniEpic paper where we use creative diversity and large language model in order to generate directly from code or in code the Python environment, the Python code, in order to define the PyBullet environment of different tasks. And here, for instance, is a type of environment that the algorithm discovered on its own. It said, oh yeah, what if you want to train your agents to overcome a complex platform moving task? And this is a solution that is generated. It's directly the Python code in order to run your PyBullet simulator. And here are some of the examples that we have. So we are like, can you just push a stack of cubes? Can you, I think this one is a dodgeball arena. You have like avoiding obstacles and things like this. And the interesting aspect here is that it's creating this kind of curriculum of more and more challenging tasks as things goes on. And you have some very creative, challenging problems like tackling a buzzy table restaurant service. You have here bounce shot scoring. You have some, where is it? There's a dodgeball, like push a ball, push 2 balls into separate goals while avoiding static obstacles, things like this. And all of this was not defined by humans. It was directly generated by LLMs, and you can leave this algorithm to run for a very long time until finding all the different problems that your algorithm or your robot need to solve in order to become very versatile and generate. So that's the end of my presentation. I hope you enjoyed it, but before ending, I would like just to thanks all and to show you all the great collaborators that I have. So that's my postdocs and PhD students from my lab, and all the work you have seen today is coming from their minds. And I hope that I managed to convince you that machine learning can teach robots to face unexpected situations, that we can use learning skills directly on real robots. We can actually cross the scene to real robots, scene to real problem quite easily, that we can leverage open-ended research, and especially the creativity of quality diversity to find unexpected solution, and that some of our work, and especially in technology, can have a direct impact to the real world. So thank you, and if you have any question, I will be more than happy to answer.